My name is Paolo Bonzini. I work at Red Hat on KVM and QEMU, and the topic of my talk is going to be the truth about QEMU's bloat, or how I learned to stop worrying and love QEMU. So why this talk? I'm going to show a few questions that people ask me, and probably people have also asked some of you, such as, for example, why is it worthwhile to invest in QEMU? What's going on with QEMU? Is it not secure because it's written in C, or is it not secure because it has a floppy disk controller? So let's start with size and bloat. Is QEMU big? And the answer then is absolutely yes. It's a large program. There's no denying that's just a numerical thing. If you run git command like ls3, you will find that excluding submodules, which are mostly firmware, so we can kind of ignore them, and only counting C files, there are 2,800 files, more than 1.5 million lines of C code. Of these, some are tests, but still it's a lot of code, and it doesn't even count header files, build scripts, test scripts written in other languages, such as QEMU tests, test data, and so on. The question that you really want to ask yourself, however, is not whether QEMU is big, it's whether QEMU is too big. And then the answer is maybe. Some people may answer yes, some people may answer no, some people may answer I don't know, and those are the best. So let's see how you can give a sensible answer to this question. First of all, how many people of you think QEMU is too big? Okay, I see that at least the cloud hypervisor guys show the strength of their convictions. But the first question, but other people are not like very much convinced that QEMU is too big, so that's a good start. But still, the first question, if you think that QEMU is too big, it's different to say whether QEMU is too big for your use case or in general. And for example, people that are working on Linux, of course, believe that QEMU is too big for their use case. It makes no sense to use QEMU for Linux. So in that case, there's like, QEMU is not just too big, it's just not the right solution to the problem. The next question that you should ask yourself if you think QEMU is too big, is why do you care about size? And we will go into this a bit later, but there are many reasons why size can be a problem. Or maybe you are thinking that you care about size, but QEMU is not too big in that respect. So for you, QEMU is not too big. The next one is, do you know how to measure size? Because sometimes you may look at the metrics like the 2,800 source code files and think QEMU is too big, but actually that's not the way that you measure size for other reasons that I will go into detail later. Then, even if you know how to measure size, have you measured it, or have you just heard from the grapevine that QEMU is too big? This is another error that many people make, not just with QEMU in general. Like, hearsay is not often the best source of information. And finally, the thing that you have to ask yourself is whether QEMU's complexity is essential or accidental, whether QEMU is just big because it has to do complicated stuff. So let's look, for example, at what QEMU can do. QEMU can emulate other processors, emulate even your processor. You can run QEMU with features that your processor doesn't have, because it's not any different to emulate an x86 processor on x86 or emulate an ARM processor on x86. QEMU can run old operating systems, probably not too old operating systems, but let's say that for the last 20 years, you should be good. It can run foreign Linux binaries emulating processors. So for example, run BusyBox for ARM on x86. And it can also use a bunch of accelerators for CPU virtualizations. Usually only one of them, because you usually have only one KVM on Linux, WSP on Windows, and so on. But it has support for 4 virtualization hypervisors: KVM, Hex, HVF, which is hypervisor framework from Apple, and the Microsoft WSP. So the first thing that you have to do if you think that QEMU is too big is try to understand your use case. For example, if you need to emulate your processor, you need to run old operating systems, but maybe you don't need to run foreign Linux binaries. You don't need to emulate ARM, or vice versa. You need to emulate ARM, but not x86. And possibly you want to use CPU virtualization. What you do is just you build your QEMU with a target list. It will only build one QEMU binary. And this is, for example, how some Linux distribution configure QEMU, and this means that you cut away like 1 million lines of code in one single file swoop. And perhaps you don't even need to emulate your processor. In that case, there is this handy -- disable -tcg, and you only get support for KVM or whatever virtualization technology your operating system support. So this is just a simple example of how you can make QEMU smaller. And so the right question to ask, based on all the questions that I presented before and this simple example, is whether your QEMU executable is too big. So whether you have configured QEMU in an optimal way for your use case, and now is it still too big or not? The other question to ask is how the size affects you. Like, does that mean that you have more attack surface? Does that mean that your disk and memory footprint is going to be larger and you want absolute, the best density of virtual machine on your host? Do you care about startup time? Do you care about number of bugs or vulnerabilities that you have to fix and the maintenance cost of them? Do you care about what your customer can do and what weird things they can report? And also the cost of auditing for security if you want to be sure that you don't run into ugly vulnerabilities or minimize number of ugly vulnerabilities that you want to have, that you will have to update the host for. So first of all, let's start with attack surface. QEMU has a huge attack surface. Every program with 1.5 million lines of code is going to have a pretty significant attack surface. For example, it has guest device drivers, can attack the host device emulation code. The management interface can be attacked with buffer overflows, whatever. There's JSON parser. It's not huge, but it's just, the JSON parser is just the beginning. Migration data is a pretty bad one because it loads data into sysstructs, and it's all done with introspection and stuff like that. And it's also a perfect way to get buffer overflows in QEMU. Image formats, same, full of pointers, full of stuff that can go wrong. ELF starts to be a bit more niche, but there have been bugs in parsing kernels that you pass to QEMU to start your guest without like grab. And finally, for example, the VNC server or other ways of interacting and providing the user with a console. These are all attack surface of QEMU. On the other hand, they aren't all the same. On a properly configured, let's say, IaaS, infrastructure as a service host, the management interface should absolutely not be visible to your tenants. The migration data should not be visible to your tenants, although they might be able to trigger bugs through the guest. So image formats should not be visible, but you should still make sure that they cannot trigger some weird detection code and perhaps access host files. ELF parsing should probably not be visible. And anyway, it's something that you can also vet in advance with your own parser. VNC server depends on the use case. Some cloud providers provide the VNC console, some don't. So anyway, this doesn't mean that this means that for every vulnerability that is in QEMU, what your vendor tells you about the importance is not what importance the vulnerability has for you. it's of course something that you want to patch, but maybe not something that you scramble and reboot all your machines for. So let's look at the top 100 vulnerabilities reported for QEMU, going back to like 2010 more or less. And if you look at them, 65 were not guest exploitable. 3 were not in QEMU at all, actually. The 2 of them were in the QEMU guest agent, and 1 was actually in KVM in the kernel. 5 did not affect x86 KVM guests. 3 were stuff like being able to access host file systems through symlink vulnerabilities, stuff like that. And of these all that remain, only 6 actually would have affected the cloud provider in a really bad way. So also, the most recent of these 6 was reported 3 years ago. So this means that absolutely QEMU has a bit more work to do because it's written in C. But my impression is that we're doing a decent job, and the attack surface is something that you should evaluate carefully, because the attack surface of QEMU is not that big in practice, because it has a lot of eyes looking at it, and a lot of security fixes have already been applied, and then a lot of whole classes of security vulnerabilities have also been fixed by having better infrastructure in the code. So regarding the attack surface, before caring about QEMU size, what you should ask yourself is whether your network is secure, what data your customer provides to you, and how you can vet it outside QEMU if needed, how you sandbox your guests so that you are protected from file system symlink attacks and stuff like that, and whether your kernel is up to date, because if your kernel is not up to date, and you have sandboxed the QEMU properly, actually KVM may end up being a much more juicy target for attacking. And that said, QEMU is a big program, and compiling less code is the perfect way to reduce the attack surface. So we want to hear from you. We want to hear what code you would like to be configured out. And if you can send patches that is perfect, you just have a suggestion that is also very good. The next one is footprint and startup time. I'm putting them together because you can measure them more or less with the same tools. QEMU residence set size, binary size, number of shared libraries that are linked. And if you look at the QEMU RSS, more or less it's 21 megabytes for the least capable target in QEMU. For that particular target, there are so few emulated devices that even if you add a CPU and an actual hardware board, the RSS doesn't change at all. For x86-64, just the amount of code in QEMU is bigger, of course, and that's worth 6 megabytes. The cost of a PC machine type and having a CPU is 6 more megabytes. The cost of using KVM instead of a fake CPU is 0, so that's a good thing. And the cost of adding a GTK interface is 30 megabytes. So just by not having a graphics card, for example, you can basically cut the QEMU RSS in half and double the density. Double the amount of RAM that you can give to your guests instead of wasting it in QEMU. But actually, even that is not entirely true. So, because you should be careful about, for example, how you measure RSS. Because text, the binary code of QEMU and any binary that you run is shared across multiple VMs. The binary code of shared libraries is shared across all programs that use that particular library. So for example, if systemd uses glib, then the fact that QEMU uses glib is completely coming for free in terms of memory occupation. Also, not all text in a shared library will be memory. You can have a huge library, but maybe you don't even touch anything until you hot plug something that requires that particular library. And also measure not the time to the first guest instruction, but the time to the first non-firmware instruction. Firmware code runs as fast as hardware and is less security sensitive. For example, the extreme case is yesterday's talk where Alex was putting a whole emulation inside the guest firmware because it's less security sensitive target. So most of the memory footprint is actually shared. The QEMU binary from Fedora 30 is 12 megabytes big. It loads 99 shared libraries, which is another 43 megabytes. You can find here a command to measure it. But actually, the RSS was only 27 megabytes. So the sum of this is 55. It means that half of the code in QEMU is never loaded into memory even. And in fact, QEMU is already modular. There are QEMU backends that you can load from shared objects. And this linked to some 200 megabytes more. Go figure what Ceph is doing with the 130 megabytes SO. So if you don't need these modules, just do not install them at all. And finally, dependencies can be configured out. We have a total of 176 shared libraries for a non-modular build, but a minimal build will have only 16 shared libraries with an RSS that is even reduced from 27 to 16 megabytes. And these are the libraries that you have. This is stuff that you are going to have running anyway in your system. It's just libc. The middle one is stuff that you probably have in your system. Pixman is probably a bit on the borderline, but I will still put it in this category. And the things that remain, the weird libraries that QEMU uses, they are so small that you might even link them statically if you want. It's seccomp, AIO, NUMA, and zlib. They probably don't even total 1 megabyte altogether. Just link them statically if you want to bring the number further down. And finally, another important one is having less bugs to fix, having less stuff to audit, having less calls from customers. So for this, again, you need to know your environment and your use case. Your customers may not need to use SDL and GTK+. Maybe they only use something like VirtViewer to show a VNC console. Maybe your customers need a VNC console because they are running Windows guests, but they don't need audio backends. And Pulse Audio is also a huge amount of shared libraries. And it may increase the RSS, increase the startup time, and so on. Also, which devices will be configured in your virtual machines. And for example, you may decide to build a custom QEMU that only has the boards and devices that you care about, let's say only Q35. It has only a few devices, most of them actually shared with other targets. So VirtIO, some PCI device and the PCI core, SCSI devices, ACPI, but no weird emulated devices from the 90s. And perhaps only a few backends, so no SPICE and only VNC, no QED and only QCOW2, and of course RAW is always useful to have. And this will be a smaller QEMU that you can build to reduce your attack surface. How do you do that? We've already seen configure arguments for most of they work for most of the backends for the accelerator or the targets. And also some features, such as, for example, block device replication can also be compiled out using configure arguments. There is also another less known feature. It's called default configs, and it's where you go and remove boards and devices. It was actually introduced a long time ago, exactly because Red Hat had this same problem of not wanting to ship insane, unsupportable devices to customers. And we revamped it this year with automatic dependencies in a kconfig-like style, where you just have to say, I want VirtIO SCSI, and it will bring in, by default, the SCSI disk and SCSI CD-ROM emulation, for example. So this is what default config file looks like. It has a first section with commented lines, and this is where you uncomment the lines and disable these optional devices. And The second part is the boards. These are by default instead enabled, and you comment them if you don't want a particular board. But this is just only providing a small part of the power of configuring our devices. What you can do is also configure with this option, -- without default devices, and then you get to specify only exactly the devices that you want. You will get the hard dependencies of those devices, but you will not get anything not default. So with the brand new micro VM machine type that was committed to QEMU like the day before yesterday, you could have a machine that has a ISA serial port, an ISA watchdog, and a bunch of virtual devices, and that's it. And this will give a smaller QEMU binary with a size that is more or less 40% of a full x86 binary. And you can get further down by disabling features. Finally, then very quickly, let's talk a bit about whether QEMU's complexity is essential or accidental. What does this mean in the first place? Essential complexity is a property of the problem that you are trying to solve, while accidental complexity is a property of the program that solves that problem in this particular case. And what seems accidental complexity to you now, if you look at QEMU code, may become essential tomorrow. You may say that it's pointless for QEMU to support hot plug, but maybe tomorrow you encounter a use case where hot plug is just your bread and butter. Or maybe it's just that you don't know the problem very well, and it's already essential. So this is certainly accidental complexity. Like, it's working around the limitation of the programming language that we're using is accidental complexity. It happens in C, Perl, Python, Rust, Go, whatever. On the other hand, this is not accidental complexity. The fact that QEMU can run more than one I/O operation, yes, there are CPU-bound workloads where it's hardly a thing to have I/O at all, and you can live with one I/O operation, but in some cases, instead, it may be something that makes your guests really, really slow. And so the fact that QEMU can do more than one I/O operation at the same time on a disk, in my opinion, is essential complexity. Being able to encrypt the serial port console is also essential complexity, in my opinion. Hot plug, it's debatable, but for example, if you look at something like kata containers, hot plug is, for better or worse, something that they have to deal with, and you cannot get the full kata containers feature set without having hot plug support. Now, kata containers may not need live migration, but live migration is certainly a big part of a lot of cloud stuff. And it comes with a big baggage, because if you want to live migrate, you probably want stable CPU models after a hardware upgrade or after migrating to a different machine. And you want stable hardware models in case you have a VMM upgrade, so that you can also use live migration to do rolling updates. And also, booting a distribution kernel, maybe it's a bit debatable whether it's essential complexity. On the other hand, for other hypervisors such as Firecracker, booting a distribution kernel is not something that you want. They're okay with building their own kernel, fair enough. We also now, with the micro VM machine type, have something that needs a specially compiled kernel, so it's certainly not part of essential complexity for all use cases. So what can we do better? We can do multiprocess split of QEMU, which will increase the complexity, of course, but on the other hand, will reduce the attack surface. So if the way that you measure size is attack surface, then great, multiprocess split is for you. If what you care about is complexity of the code, then multiprocess split is something that you may not like. So again, depends on the use case. We are, at least now, considering the host user as the multiprocess interface, even though there are patches on the list to, for example, do multiprocess QEMU PCI devices. And also, having an out-of-process block layer will be able to give improved performance and finer grain secom filters, so improve the security in multiple access. We would like to have even easier configuration. Kconfig was a big step in that respect, but we would like users to know exactly, just by looking at the default configs file, which PCI devices are enabled by default and which virtual devices are enabled by default, not just the onboard devices. And also something that could replace the configure script using text file configuration files also for the host components. And finally, better documentation is always high in the wish list. Unfortunately, not very high in the to-do list, but still, with QEMU 4.0, we had an initial port of documentation to Sphinx, which greatly improves the usability. We are thinking of how to reorganize the manual and put all the material there in a way that is easier to consume, and also document the best practice for running QEMU securely, which includes making a smaller QEMU only as big as you need it. So the conclusion is know your use case, know your customer, which is related to knowing your use case, and if you have doubts, talk to developers. Thank you very much.